Hello viewers, in this session we will discuss about Mobius transformations and some of their properties. Let us start with the definition. A transformation of the form T of z is equal to A z plus b by C z plus d, okay, where A, B, C, D belongs to complex numbers, okay, is called a linear fractional transformation. And I have deliberately withheld specifying the domain and range of this function. Well, these depend I mean the domain depends on the numbers c and d. If in addition a d minus b c is non-zero, okay, then T is called a Mobius transformation. Okay. So, now let us consider a Mobius transformation. Consider T of z is equal to A z plus b by C z plus d, where A, B, C, D are complex numbers with A d minus B c non-zero. Okay. So, that will be our subject of discussion. Okay. And if c is 0, if the constant c there is 0, then t is a function, okay, from c to c, i.e., the domain is all of the complex numbers, and then the codomain is the complex numbers, of course. Okay. And if c is non-zero, then it has to miss a point, okay, then the function t is defined on c minus the point minus d by c, because at minus d by c this function the denominator in the function has a value 0. Okay. So, and then this maps to c. So, it is sort of a split case here. So, what we can do is we can do better, we can extend the definition. Okay. So, what we can do is we can extend the definition of this function, okay, onto the complex plane union the point at infinity. Okay. So, using the point at infinity, okay, we will see that this is the most natural setting for these functions. Okay. So, we will see actually that all of these functions are actually bijection. So, first I should define the extension. Okay. So, if c is equal to 0, okay, define t of infinity is equal to infinity, because now our domain contains infinity, I have to specify where infinity goes to. So, in the event that c is 0, we will define t of infinity as infinity, okay. And if c is non-zero, then I have to modify two definitions. Okay. So, define t of minus d by c, which we omitted earlier, okay, define that to be infinity, okay, and define t of infinity to be the point a by c. Okay. In the earlier case, that point a by c would never have been taken if we restrict ourselves to the domain c minus d by c, c minus d by c. Okay. So, with this extension, what we are going to show is that firstly, then with this extension t from c union infinity to c union infinity is a function okay, and we are going to show that this is actually a bijection. Okay. So, if it is well defined firstly. So, if A z plus B by C z plus D, okay, is equal to A z 1 plus B by B plus divided by C z 1 plus D. Okay. This happens if and only if A z plus B times C z 1 plus D is equal to A z 1 plus B times C z plus D. Okay. And that happens if and only if, let us multiply it out and there will be cancellations. So, A C z z 1 plus B D plus A D z plus B C z 1 is equal to A C z z 1 plus B D plus A D z 1 plus B C z. Okay, when we multiply this out, and then there will be cancellations, and after cancellation, this is if and only if this cancels with this cancels with this, then we are left with A D minus B C times Z is equal to A D minus B C times Z 1. This is if and only if Z is equal to Z 1, because A D minus B C is not equal to 0. Okay. And so, this works for all of this works for Z belongs to well, Z belongs to C if C is not equal to or C is equal to 0, okay, and Z belongs to C minus D by C, okay, if C is not equal to 0. Okay. If C is equal to 0 for infinity, or if C is not equal to 0 for the case of minus d by C, etcetera, and infinity, we show this property separately. We can show that this holds, the image of T is equal holds. Okay. So, all in all, okay, so except for some cases, we have shown that T is 1 to 1. Okay. So, T is 1 to 1. Okay. So, the viewer is informed here that there are some cases I have already spoken of, which I have not covered, but that is an easy exercise. One can show that then T is 1 to 1, one can conclude T is 1 to 1. Okay. So, then we can also show that T is onto why is T onto C union infinity, that is what I mean. Okay. So, we will do this in two cases. Let W belong to C union infinity, okay, or let me take W belonging to the finite complex plane. Okay. If C is not equal to 0, okay, in the first case, if C is not equal to 0 and suppose W is not equal to A by C. Okay. So, then in this event that W is not A by C, then we can work out what W is by setting and is W equals A z plus B by C z plus D. Okay. We can this can be solved. This can be solved, okay, for Z. What we get is Z is equal to B minus d W. Okay. Multiplying it out and factoring out a Z, we get Z is B minus d W divided by W C minus A, okay, and we have assumed that W is not A by C. Okay. W is not equal to A by C. In this event, Z is this particular number. Okay. If W is equal to A by C, we already know that in this event that f of infinity is equal to W. Okay. So, in the case that C is non-zero, we have shown that I apologize, I am using this function is T, okay, T of infinity is W. Okay. So, we have shown that so T is onto. So, T is onto if C is non-zero. In the event that C is 0, then also we can show that this is onto. If C is 0 and if W belongs to C, okay, we have let W belong to C, okay, then we can directly say that W is equal to A z plus B by D, okay, which implies that Z is equal to d W minus B by A. Okay. Notice that A cannot be 0 if C is 0, because A d minus B C is non-zero. Okay. So, so this happens, okay, and this Z gives you T of Z, okay, for this Z T of Z is equal to W. Okay. And if W is equal to infinity in this case when C is equal to 0, okay, we already know that we define T of infinity to be infinity. Okay. T the extended definition, refer to the extended definition, we said T of infinity is infinity if C is 0. Okay. So, in this case T of infinity is infinity. Okay. So, T is onto in this case as well if C is equal to 0. So, in either case, T is onto. In either case, T is onto C union infinity. Okay. T is 1 to 1 and onto. So, it is a bijection from C union infinity to C union infinity. Okay. So, T is a bijection. So, we will see that these Mobius transformations are not only bijections from C union infinity to C union infinity, but they also preserve the complex structure of C union infinity. Okay. So, what one means by that is at least to start with, a Mobius transformation maps, we will see that it maps circles in C union infinity, which we call a Riemann sphere, okay, to circles on C union infinity. So, circles, the images of circles are circles, okay, and not only that, we also have the fact that it maps the disk bounded, okay, by this circle, okay, onto. So, T maps a disk bounded by the circle onto a disk bounded by the circle in a very nice fashion. Okay. So, that we are going to see now. Okay. So, firstly I have to show that T maps circles onto circles. Okay. In order to do that, let me first begin with some more facts about Mobius transformations. Okay. So, since T is a bijection, T inverse from C union infinity to C union infinity is well defined. Okay. So, case 1, if C is equal to 0. So, likewise I mean corresponding to the cases for T, we will have a case for T inverse. If C is equal to 0, then T inverse of W is d W minus B by minus C W plus A, okay, for W not equal to infinity, and T inverse of infinity is of course infinity. Okay. And case 2, if C is not equal to 0, okay, then T inverse of W is once again d W minus B by minus C W plus A, okay, and T inverse of this is true for W not equal to infinity and W not equal to minus D by C, and T inverse of infinity is A by C and T inverse of minus D by C is infinity. Okay. So, we just write down the corresponding cases, okay, for T inverse. Okay. So, that is the formula we have for T inverse given T. Also, we will note that this notation for a Mobius transformation A z plus b by C z plus d is not unique. Okay. So, so T of z you will notice is A z plus b by C z plus d. Okay. It can also be written as A lambda z plus b lambda divided by C lambda z plus d lambda, okay, where lambda is a non-zero complex number. Okay. Not only that, it is actually true, one can solve this as an exercise. Okay. So, one can show that if T z is A z plus b divided by C z plus d is A 1 z plus b 1 divided by C 1 z plus d 1. So, if you can specify a Mobius transformation in two different ways, notice here we have A d minus B c is non-zero, and so is A 1 d 1 minus B 1 C 1. Okay. So, then there is a lambda, okay, lambda not equal to 0, lambda belongs to C, okay, such that A 1 is equal to lambda A, B 1 is equal to lambda B, C 1 is equal to lambda C, and D 1 is equal to lambda D. Okay. So, one can try that as an exercise. So, the specification of T in this form is not unique. Okay. So, also we can decompose a given Mobius transformation as a composition of certain elementary kinds of Mobius transformations. Okay. For that purpose, define 4 kinds of elementary transformations. Okay. T of z is z plus a is called a translation. Okay. So, for some a belongs to C, and T of z is equal to a z, a times z, okay, a non-zero is called a dilation. Okay. And T of z is equal to e power I theta z is called a rotation, and T of z is equal to 1 by z is called inversion. Okay. So, all these are actually Mobius transformations themselves, special kinds of Mobius transformations. Okay. And what we are going to show is, we are going to give the following proposition, that if T is a Mobius transformation, okay, then T can be written as a composition okay, the composition of translations, dilations and inversions. Notice that rotation is actually a form of dilation, where the constant a has modulus 1. Okay. So, the proof of this fact is easy. Okay. What we can do is, suppose C is equal to 0, then it is easy. Then T of z, what does it look like? T of z looks like a by d z plus b by d, which we can immediately see is a composition of a dilation and then a translation. Okay. So, let S 1 of z is equal to a by d z, and S 2 of z is equal to z plus b by d. Okay. Then S 2 composed with S 1 of z is going to be equal to T of z. Okay. If C is non-zero, okay, then let us tinker with the formula for the Mobius transformation and get a particular form, and then we will see how we can write T as composition of these elementary Mobius transformations. Okay. So, what I am going to do is in the numerator I am going to get a C z plus d, so that I can divide. So, I am dividing the denominator into the numerator. So, I will write a by c. Since c is not 0, I can write the numerator as a by c times C z plus d plus b divided by C z plus d. I apologize, I need a minus. I have added a d by c. So, I subtract a d by c and then I have a plus b. Okay. So, then now what I can do is I can write this as a by c minus or plus minus a d plus b c. Okay. I am clearing the fraction in the numerator, okay, and then I am multiplying the c into the denominator to get c squared z plus d c. Okay. So, now I see what the form is. Okay. So, this can be written as a by c plus 1 divided by c squared by b c minus a d. Notice b c minus a d is non-zero, okay, z plus d c divided by b c minus a d. Okay. So, if we let S 1 of z is equal to the dilation by c squared divided by b c minus a d times z, okay, and then let S 2 is equal to translation by d c divided by b c minus a d, okay, and S 3 to be the inversion, S 3 of z to be 1 by z, and S 4 of z once again the translation by a by c. What we have is S 4 composed with S 3 composed with S 2 composed with S 1 of z is going to be your a z plus b by c z plus d, okay, which is your t of z. And notice that these compositions also work for those other exceptional points minus d by c or infinity, etc. Okay. So, one can verify by substitution that these compositions also respect those special definitions. Okay. So, that proves this proposition. So, next we are going to see some other properties of Mobius transformations. Okay. So, namely fixed points. Okay. So, for the purpose of this discussion, I am actually following the book by Conway. One can refer to the book by John B. Conway, okay, which is listed in the textbooks or references. And so, notice that a Mobius transformation by the following analysis will have some fixed points. Okay. So, firstly, if c is equal to 0, okay, then t of infinity we know is infinity. Okay. So, on C union infinity, and this there is one fixed point if c is little c is equal to 0, okay, and then also a by d z plus b by d is equal to z. Let us equate the Mobius transformation t of z is equal to z. Okay. So, t of z, now since c is equal to 0, it looks like a z plus b by d, okay, and then if that is equal to z, we have this equation which upon solving gives us a by d minus 1 times z is minus b by d. Okay. So, if now there are cases, case 1, if a is equal to d, okay, then you get 0 equals minus b. Okay. So, then there are no other fixed points. So, in the event that C is equal to 0 and if A equals D, then there are no other fixed points. Okay. Case 2, if A is not equal to D, then we can solve this equation to get Z equals minus B by A minus D. Since A is not equal to D, the denominator is not 0. Okay. This is the other fixed point. Only one other fixed point we get from solving T of Z is equal to Z. Okay. So, there are at most two fixed points in the case C equals 0. Okay. If C is not equal to 0, okay, what we have is then A Z plus B by C Z plus D, equating this to Z. What we get is C Z squared plus D minus A times Z plus or minus B is equal to 0. Okay. So, we get a quadratic equation. Okay. So, this has at most two solutions in C. Okay. So, the summary is there are at most two fixed points, whether C is 0 or C is non-zero. Okay. So, a Mobius transformation, okay, which fixes 3 points, okay, has to be the identity. Okay. Why is that? Well, identity fixes every point, okay, and by the above analysis you can have at most two fixed points for a Mobius transformation. Okay. So, the only Mobius transformation which fixes 3 or more points, okay, 3 or more points has to be the identity Mobius transformation. Okay. So, the identity, what is that? I of Z is equal to Z. Okay. In this case, A, D are 1 and B and C are 0. A equals D equals 1, B equals C equals 0. Okay. And in that event, every point in the finite complex plane and the point at infinity are all fixed. Okay. Okay. So, suppose Z 1, Z 2, Z 3 are distinct points in C, okay, and or you could actually pick C union infinity, points in C union infinity, okay, and suppose T of Z 1 is equal to W 1, T of Z 2 is equal to W 2, T of Z 3 is equal to W 3. Now, suppose S also has this property. Okay. So, suppose S of Z 1 is also equal to W 1, S of Z 2 is equal to W 2 and S of Z 3 is equal to W 3. Okay. S is a Mobius transformation. Okay, transformation. Okay. Then you notice that apply T inverse circle S, okay, to any of the points Z 1, Z 2, Z 3. Okay. What you get is this is of Z 1 is equal to Z 1, okay, and T inverse of circle S of Z 2 is equal to Z 2, etc. T inverse of circle S of Z 3 is equal to Z 3. So, it fixes 3 points. T inverse circle S is also a Mobius transformation, okay. And so, well, actually that is an exercise that if T and S are Mobius transformations, Mob for short. Okay. Then the composition of these is also a Mobius transformation. That is an easy exercise. The viewer is advised to solve this exercise. It is an easy exercise. Just compose and show that the condition A d minus B c for the new constants which arise when you compose, okay, also holds. Okay. And when you show that T inverse circle S will also be a Mobius transformation and it fixes Z 1, Z 2, Z 3. So, what that says is that so T inverse circle S is equal to the identity transformation. Okay. So, which implies S is actually equal to T. Okay. So, if you know the image of 3 points via Mobius transformation, okay, then the Mobius transformation is determined. Okay, that is what this means. So, owing to this property, what we are going to do is we are going to get another representation of these Mobius transformations. Okay. So, here is a definition. Okay. So, let Z 2, Z 3, Z 4 belong to C union infinity. Okay. Since the image of 3 points determines a Mobius transformation, okay, what we are going to do is we are going to make the following definition, define T of Z as Z minus Z 3 divided by Z minus Z 4 times Z 2 minus Z 4 divided by Z 2 minus Z 3. Okay. This additional adjustment factor if all Z 2, Z 3, Z 4 belong to the finite complex plane, okay, not infinity, finite complex plane. Okay. So, notice that when you substitute, I mean this is a function of Z, the right hand side is a function of Z, and when you substitute Z 3, the numerator is going to be 0 in the first factor. Okay. So, you get 0. When you substitute Z 4, the denominator is going to be 0. So, you get infinity, and when you substitute Z 2, there is a cancelling factor, the second one. Okay. So, the second one cancels with the first factor to give you 1. Okay. So, what this definition does is T of Z 2 is 1, T of Z 3 to 0 and T of Z 4 to infinity, or T of Z 4 is infinity. Okay. And likewise, you can for other cases when Z 2, Z 3, Z 4 are not in the finite complex plane, for other cases you can make equivalent definitions Z minus Z 3 divided by Z minus Z 4 if Z 2 is infinity. Okay. And T of Z define that to be Z 2 minus Z 4 divided by Z minus Z 4 if Z 3 is infinity, and T of Z define that to be Z minus Z 3 divided by Z 2 minus Z 3 if Z 4 is infinity. Okay. So, in any of these cases, well, not two of them can be infinity, only one of them is allowed to be infinity at a time. Okay. So, if you pick Z 2, Z 3, Z 4 belongs to C union infinity, okay, let these be distinct points. Okay, that is the main assumption. Okay. And then you define T to be like that. Okay. In any of the above case, what we observe is T of Z 2 is 1, okay, and then T of Z 3 is 0 and T of Z 4 is infinity. Okay. And T is the unique Mobius transformation okay, with this property. Okay. From what we have said above, if there is any other Mobius transformation which sends Z 2 to 1 and Z 3 to 0 and Z 4 to infinity, okay, given 3 fixed points Z 2, Z 3, Z 4, then it has to equal S as a T rather. Okay. So, by that property T is the unique Mobius transformation. So, owing to this we are going to make a definition. We will say that if Z 1 belongs to C union infinity, okay, then the cross ratio of okay, or I will say the cross ratio Z 1, Z 2, Z 3, Z 4. Okay. So, that is the notation, okay, is the image of Z 1, okay, under the unique Mobius transformation which takes Z 2 to 1, Z 3 to 0 and Z 4 to infinity. Okay. So, we have defined such a T, okay, and then the cross ratio Z 1, Z 2, Z 3, Z 4 is essentially the image of Z 1 under this Mobius transformation. Okay. So, we will see that this notation or this quantity is very useful. Okay. We will capture some properties of this cross ratio, okay, and we will see that it is useful. So, firstly, some trivial examples. If you take Z 2, Z 2, Z 3, Z 4, for example, the cross ratio of Z 2, Z 2, Z 3, Z 4 is going to be 1, because the image of Z 2 under the Mobius transformation, which takes Z 2 to 1 and Z 3 to 0 and Z 4 to infinity, has to be 1. Okay. And likewise, the image of the identity image of a point Z under the identity Mobius transformation is itself, okay, for all Z belongs to C union infinity. Okay. So, the identity transformation is now denoted by the cross ratio Z 1 0 infinity, because in this case this represents 1 goes to 1 and 0 goes to 0 and infinity goes to infinity. Okay. And there is only one transformation which fixes 3 points, namely the identity. Okay. All right. So, these are some trivial examples, okay, and here is a proposition. Okay. If Z 2, Z 3, Z 4 belong to C union infinity, okay, are distinct, okay, distinct points, and T is any Mobius transformation, okay, then the cross ratio Z 1, Z 2, Z 3, Z 4 is equal to the cross ratio T Z 1, T Z 2, T Z 3, T Z 4. Okay. So, for any Mobius transformation we have this property. Okay. So, that is the relation between any other Mobius transformation and a cross ratio. Okay. The proof of this is very simple, but what we are going to do is we are actually going to use this proposition to explore some properties of Mobius transformations. Okay. So, let S z be the Mobius transformation which is given by Z, Z 2, Z 3, Z 4, and by the exercise which I left to the viewer, M is, let M equals S circle T inverse. T is a Mobius transformation, T is any Mobius transformation, but the inverse to any Mobius transformation exists. Okay. We have seen that T inverse is also a bijection between from C union infinity to itself. Okay. So, define a new Mobius transformation which is composition of S circle T inverse. Composition is also a Mobius transformation by this exercise. Okay. So, so let M equals S circle T inverse, and notice that M of T Z 2, okay, which is S circle T inverse circle T of Z 2, this is equal to 1. Okay, because S of Z 2 is 1, and likewise M of T Z 3 is equal to 0, and M of T Z 4 is equal to infinity. Okay. So, so of course, S T inverse of Z, okay, which is M of Z. Okay. M of this quantity is 1, this quantity is 2, and this quantity is infinity. So, M of Z itself can be written as Z comma T Z 2, T Z 3, T Z 4, because the image of T Z 2 is 1 and T Z 3 is 0, and that of T Z 4 is infinity via M. Okay. So, from here what we have is S T inverse of Z is this. So, S of quantity in C union infinity is equal to Z comma T Z 2, T Z 3, T Z 4. Okay. So, what this means is that if I substitute for Z, if I substitute T of Z, what I get is T of Z, T of Z 2, T of Z 3, and T of Z 4. Okay. So, I am actually writing the image as T Z. Okay. I have been using that before. Okay. So, what this tells us is T inverse circle T is identity. So, this gives us the LHS is S of Z. This is T Z, T Z 2, T Z 3, and T Z 4. Okay. And this is what we wanted. So, so it completes the proof of this proposition. And there is yet another property that we will need. So, here is another proposition. Okay. If Z 2, Z 3, Z 4 are distinct in C union infinity, and W 1, W 2, W or W 2, W 3, W 4 okay, are also distinct, okay, then there is one and only one Mobius transformation such that S Z 2 is equal to W 2, S Z 3 is equal to W 3, S Z 4 is equal to W 4. Okay. And the proof is really easy. Okay. If you let T Z is equal to Z, Z 2, Z 3, Z 4. Okay. So, the idea is Z 2, Z 3, Z 4 go to 1, 0 and infinity, okay, and you have W 1, W 2, W 3, W 4 distinct, these go to 1, 0 and infinity. This is the schematic. Okay. So, T is this, I am going to call this as M of Z is equal to Z W 2, W 3, W 4. Okay. So, M is the one which takes W 2 to 1, W 3 to 0 and W 4 to infinity. Okay. Then you notice that let S okay, and let S equals M inverse circle T. Okay. So, M inverse circle T takes okay, and takes W2 or Z2 to W2, Z3 to W3, okay, and Z4 to W4. Okay. So, it satisfies the requirement for S, okay. And if R is also, okay, another Mobius transformation which satisfies the requirement, namely it takes Z2 to W2, Z3 to W3 and Z4 to W4, okay, then R inverse circle S fixes 3 points by the previous kind of argument. Okay. R inverse circle S fixes 3 points Z2, Z3, Z4. Okay. So, implies R inverse circle S is the identity transformation which implies R is equal to S. Okay. So, this is unique, okay, and your M inverse circle T is what is wanted. So, that is the idea, you take Z2 to 1, Z3 to 0 and Z4 to infinity, okay, and then go back via M, 1 goes to W2, 0 goes to W3 and infinity goes to W4. Okay. So, that way you can achieve what is wanted in this proposition, okay, that S. All right. So, that gives us a way to represent Mobius transformations using cross ratios, okay, and our goal is to actually show that these functions Mobius transformations are not only bijections from C union infinity to C union infinity, but they also preserve complex structure, i.e., they take circles to circles and they take the disks bounded by these circles to disks bounded by the image circle. Okay. So, these properties will help us achieve that goal, these propositions that we proved will help us achieve that goal. So, we will continue to explore the properties of Mobius transformations. I will stop here.